Very good afternoon, all. Welcome to the class on the linked list. This is going to be our third lecture on linked list. So, in the last class, we have already discussed some basic programming on the linked list, and we have already seen that what we need to talk is insertion and deletion after a particular value. So, last time we have said to create till -1 was to be discussed, -1 was input, traversal, and insert and delete after a given value. So we have planned to do that implementation. We will have a demonstration of the same. And once we are completed with that, then we are going to continue with the remaining discussions for today's talk. So let's have a look on the program, and let's have a look on the demo code of this. So this is what you should see. Of course, first of all, let's see the create. So what we discussed was read the values till -1 is inputted. First time itself, it could be an empty list created. So if -1 is inputted for the header node itself, then I should return null, or you can write start equal to null and return start, one and the same thing. If that is not there, that means one node is guaranteedly created. This is first node created and current kept to the starting node. Subsequently, we will keep on reading and keep on adding the new node through these 4 steps, which we have already discussed last time. And based on that, every time the new node will be added and connected to the current, and current will be updated. Of course, here I have also checked whether the value is -1, so that value itself should not be read and stored, should not be itself stored into the linked list. So if the value is -1, the node will not be created and not stored at all. One more point to remember in these cases is that it is possible that sometimes malloc can fail. So there is always a good practice that you make always a check saying that if a start equal to null, it means malloc failed effectively. And that will mean your program cannot continue. So although for your programs, it will not happen, but for good programmers, it's always a good practice that you always check that if the malloc failed, then you give the message that malloc has failed, and that message is done every time whenever malloc is done. And then effectively you don't have a choice, but you have to break or you have to effectively exit. So exit 1 is the normal way we exit with an error being reported, and that can be another way where we should always do that. So for good programmers, null returned by the malloc will be meaning that the malloc failed. So it's always a good practice to do that, but mostly we will assume it works well. So ideally, yes, after this malloc also, I should check for the failure and then do that. So that becomes this logic, current updated, create function. -1 will mean stop inputting the value. Otherwise, you keep on repeating. And whenever -1 given, that is not a value to be stored. Before that, all values to be stored and linked list is ready. Remember, this -1 should not be stored. Otherwise, if you don't break here, you will reach to this loop, but you will come out of the while loop after this statement. But by that time, your -1 will also get stored. So that's why I have put this if and then break. Then traverse, simple logic, while temp not equal to null. So traverse is simple always, temp not equal to null, keep on printing and going to the next pointer. That's it. Now we say insert and delete. So insert after a val is what we discussed last time. So we said that our target will be go to the node after which the insertion is to be done. So my current pointer will be taken to start with the start or head, and it should be incremented till we reach to the corresponding pointer after which insertion is to be done. Of course, this code is taking care of invalid values also. So this condition is for checking the invalid value given for the val that is not existing in the list. But if you find not to be used, and if you want to do simple programming, of course, simple current data not equal to val, the way we discussed last time, can be done. But if you are checking for invalid, current not equal to null must be checked before the other condition, because via null, you should never attempt to access any field. So current, if not null, only then current arrow data statement should be done. I mean, if you try to put this condition after this On the other side, I mean, if you try to write it in this form, it will be incorrect. So if you write it like this, not good way, or it will be incorrect. The code can crash, especially when the current will become null. Once it has become null, this situation will be checked via this null pointer data field is being accessed. Code will crash. After that, the condition is current not equal to null, which will be violated, but that will be incorrect. So we should not do like this. So, and then because I'm saying that a better way of doing was like this, so I did like this. And if current reaches to null, I will say value not found. Otherwise, value is to be inserted, will be inserted by the standard logic, which we discussed last time. Similarly, for the delete after val, again, the current pointer has to be brought to the node after which insertion is to be done. So if invalid is not to be checked, you can simply use current data not equal to val, and because value guaranteedly exists, this condition will become true at some point of time, and then accordingly that will be happening. But if I'm checking invalid, so I'm checking if value not found, that will be also detected. If it was the last node, then also this condition will be detected separately. Otherwise, deletion will be attempted and deletion will be done like this. And delete value will be returned. So if the value was actual value deleted will be returned. Otherwise, initially I have given del val equal to -1. So that is being returned. If you want to use it somewhere, you can do that. Then here I can have repeated choices, say create, display, insert, delete, etc. And 1 for this, 2 for this, 3 for this, 4 for this, and so on. Here are some sample test cases. In the lab, I have already started with one section. Other sections also I'll share these test cases. So you must do that. There is just one correction here. This is delete 70. This data is a 70. And that is some minor correction here. So that is at one point of time. And similarly, there is one more correction that is delete after this is a 70. So that will be insert after 70, that will be done. So with this, I say now this is the way you should program it and then test it for all different cases. Having said that, now let's go back and resume with the today's discussion. So now we talk of today's talk and proceed further. So having done this, I say effectively all linked list programming is going to be oriented towards this only. More or less, we have understood the programming concepts via insert and delete after. Effectively, every time we will have these kind of operations, and all programming will be via in the similar manner. For example, today we extend the code and we try to do the same work for insertion and deletion at some position. Till now we have said this. So today we will see at certain positions. For example, to start with is at beginning. We have not discussed that code at all because at the beginning, it is never after a value. Because before that, no value exists. So if I'm talking of at the beginning, that will mean effectively I'm going to do it in the way of doing programming for the beginning in a different manner. For example, if my linked list is like this, let's say I have here 10, then I have 15, then I have, let's say, 20, and so and so. And I say, this is a start. I'm interested to insert at the beginning. That means, let's say, I want this 5 value to be at the beginning. That will effectively mean that my linked list should become like this. Now, if I want to achieve this, this code is different than the way we have done till now. In this case, one important point is start will change. Hence, we have to handle that part also. So maybe I can think of writing insert at beginning to be a separate function. Insert at begin to be written as a separate function. So what should be the parameter? Obviously, start needs to be sent. The new val, which is to be inserted, that also needs to be sent. What it should return. Earlier, we have said that it can be void because nothing else was changing. Now it cannot be void because node pointer will be required to be returned because the start will change. Then changed start should be returned back via this statement. Hence, what we are going to do is that we will require this changed start to be returned via this node start. Assuming that your list always exists, so I'm not taking of invalid cases, I'm assuming valid cases, then things are easy. I will say insert beginning effectively means I have to do something in a different manner. First step, this node to be allocated. So this is a temp node. So I will say I will declare node star temp, a local variable. If you want a variable node pointer to be declared, that is simply a variable declaration. But I want a new node also to be created along with node pointer, then I need malloc. So temp equal to malloc. Ideally, yes, we must check here if a temp equal to null, that means malloc failed. And that will mean printf and exit, the way I just said. So ideally, after every malloc, I must check that. But for most of the coding, we will not be writing this code explicitly, assuming that malloc is always working correctly. And exit one means exit from the code with error. So exit 0 means without error, and exit 1 is a standard programming philosophy to exit with error. Rest, maybe I'll not discuss at present, but yes, this is one statement which will break the execution of the program, not the function. Full program will be terminated. But yes, this is optional. We might not write every time. So step 1, temp created. This is a temp. Step 2, this data to be assigned the corresponding value. So step 2 will mean this step, temp arrow data to be given the value which we have just planned, new value. So this becomes this step. Third step, this linking to be done. So this I have to link effectively at the start. Temp arrow link to be updated. Temp arrow link to be assigned a new address. What a new address? Start, where start was pointing. Not start arrow link, because start arrow link points to 15. This is start arrow link. This points to 15. I need the temp arrow link to come to 10. That is, initially start was here, and now start has changed. So this is step 3. This was step 2. And next step, final step is start to be updated. Start has to point to the temp now. This will become the start now. So this will be step 4. And once I have updated, I must return the start. Changed start has to be returned. Why do I need changed start? Because start position has changed. From the main, how the call will come. From the main, whenever I am deciding to insert at beginning, my call will be something like this. Start equal to insert at begin. And here the parameters, for example, start itself and the new value which I want to insert. Remember, this start is being sent as a parameter which will just go there to supply the currently created linked list. But this start is getting the updated or changed start being returned. Hence, we need start to be returned and updated to be assigned to this. So we must do this, and that will mean I will be changing this. So this will become my insert at begin function. Similarly, I have to think of delete at begin. But before that, just let's verify if the list was null, if the list was empty, will insert at begin work? We have to check that. We have said valid cases, but well, that if the list was empty, insertion should work. That is a valid case. Will it work or not? Let's check. Step 1, malloc. No issues, nothing are dependent on the list. Yes, without problem. Step 2, temp arrow data. That also not an issue. That is also perfect. Step 3, we said temp arrow link equal to start. Let's check whether this statement will be correct or not. If list is empty, this should mean start is null. That we have to ensure every time that the start is null whenever the list is empty. And if that is there, it will mean this statement becomes something like this. And this is perfectly fine. Then step 4, start equal to temp. Start equal to temp. Again, earlier whatever start was doesn't matter. Now start gets a new value. And then of course return will work without any problem. So return start is also perfect. So this code will work even if the list was empty. Not an issue. Now, similarly, let's think of doing the delete at beginning. Delete at beginning also means the same process. Almost similar, that if I have this value, let's say here I have 10, here I have 15, and so and so. This is my start. Delete at begin means the 10 should be deleted. Effectively, that means I have nothing big to be done. This node should be freed. So I should have a temp variable to come here. And my start should go from this position onwards. That's it. Nothing else to be done. So start will also change. Hence, changed start must be returned. So the process remains more or less similar what we have just done. Having said that, it will mean again, if I say I have to write a function, I will say delete at begin will be the function. And now it must return a node star because a changed start must be returned. Parameters, whatever I require, let's say node star start. For the time being, maybe this enough. If I require something more, I can think of what to do. If my list is having something, first step is I have temp to be assigned to the same so that it can be freed. So declare your variable, but don't malloc. Temp is supposed to point to existing node. Temp equal to start. So no malloc needed. Pointer is created. Wherever start was, temp also points to the same value. This is a temp. Earlier, this was a start. Now, temp also points here. 10 is linked with 15 and so and so. First step done. What is next step? Effectively, start has to shift. So start has to go to the next node. Start equal to what? Start has to go to this pointer. So this pointer can be accessed as start arrow link or temp arrow link. So I can say start equal to maybe start arrow link. So if this was going to be done, again, that means start changes from here. After that, of course, node temp can be freed. But before freeing, if I need the temp data, so maybe I will have a del val variable. And I can have temp arrow data. And the deleted value, if I want to display, you can printf here. And printf del val, etc., whatever syntax you require. And after that, you have to free temp because node has been deleted and a temp is a pointer, free temp. So that is going to be your main third step. This step is if you want the value to be displayed or returned, whatever you can. And then finally what? You have to return the updated start. So return start will be must. This is must because start has changed. From the main, how the call will come? Obviously, the call will be now again something like, say, I will say start equal to delete at begin, function being called with proper parameters, and parameters are, let's say, start itself, semicolon. So this is the current list being sent, the current start being sent, and this is updated start being returned. And this will work the way exactly we have done. Now, first thing, let's say list has a single node only, one node. So deletion should work. That is a valid case. Invalid, we have not yet discussed, but invalid we will see later. One node. One node means there was only 10. And the list was empty after this. This is my start. Let's check whether my code works or not. First step, temp equal to start, no issues. Second step, start equal to start arrow link. So at second step, start becomes equal to start arrow link. Arrow link is null. So now start becomes null. Perfect. This is what we want after the first node will be deleted. If delete val to be printed, yes, can be printed. Free temp, yes, this node will be freed. Return start. Start is null. This will also work. Okay. So valid cases, all valid cases, I hope will work now. Even if list has more than one node, then also deleted. Not one node, then also deleted. Just imagine if list was empty. Of course, that's an invalid situation. We are just verifying whether that situation will work well or not. We have written the code for valid situations, but for invalid, what will happen? Temp equal to start, start is empty, perfect. Start equal to start arrow link. If it is null, via null, if you try to access any field, this is going to crash. Rule R6 will be violated of my pointers. Their pointer must point to a valid location whenever you want to see value of any field pointed by this pointer. So at this point, it will fail. Hence, for incorrect situations, this code is going to fail. Of course, I can write a separate statement. If start is null, then accordingly, I can write extra if and handle all that also. So that we have to understand. But yes, at least we must try to implement for valid cases. Okay, what if I wanted a del val to be sent back? Like in previous code, we have sent del val back. Not just printed, because in main it may be needed to be used with some other purposes, like I'm deleting a value and that same value is to be used in some other calculations, etc. So I want this deleted value to be returned back. How to do that? Earlier, I had int return where I said delete after, and then I could return via the int. But now this won't work because my node star is already being used to return for delete at beginning. Hence, I have no choice, but return type cannot be used. Then how to return? So return will mean that I need call by reference. Del val to be passed as a call by reference parameter. Those who want to try, they can try. Those who find it difficult, maybe forget this. But those who want to try, that will mean that my delete at begin function will have all whatever we have done till now, okay? Node star start, etc. being sent, okay? Along with that, I will also send one call by reference variable. And once it is being sent, this is a value which is via pointer being sent. So effectively, I will require star del val to be assigned equal to temp arrow data. Along with all other remaining steps, whatever we have done, this step will make the data being returned. And from the main, the call will mean I will have start equal to delete at begin, start being sent, and maybe if I have int val2 to be used for returned value, call by reference means you will call it with ampersand. That will mean effectively that you are going to write it ampersand val2. And once this is ready, maybe you wanted to print or whatever you wanted to do with the val2. Either print or use anywhere. So if you are returning, because return type was not available, so this is a call by reference parameter. And through pointers, we have learned already that, so you can always use it for such situations. But if you are finding it difficult, forget about this. This is optional. Those who want to do, they should try. Those who find it difficult, no problem. Just try to learn basic programming of the linked list. Now, so delete at begin, insert at begin, understood. So things are now ready. So I will say using this, now I will say, let's write a program to do insert or delete at some position. Let's say at position POS. Means, for example, I say insert at position 1. At 1 means at the beginning. Means the new node should become the starting node. And if I say, let's say insert at position 3, it means new node becomes third node. For example, if I have, let's say here 10, I have here 15, I have here 20, and let's say insert at 3, some value, let's say 33 to be inserted. That means this is your node position 1, node position 2. So I want a new node to be created, 33 to be inside this, and this should become at position 3. That will effectively mean my list should become like this. So this will become my at position 3. Effectively, what it requires I should be able to stop at position 2, and after position 2, I want to insert. Because ultimately, whenever you want to insert, you need a previous pointer. Whenever you want to insert, before that, you need a pointer always. Only through that, you will be able to insert, or otherwise, at beginning, there is a special case, and that you can do always separately. But in all other cases except special case, I will say the previous pointer always needed. So I have to always do insert after logic to be implemented. And that will mean for position, any position, I have to stop somewhere before. So if I assume that my position is always valid, that will mean no invalid cases to be handled. Then that will mean, let's say I have a linked list like this, 10, 15, 20, let's say 20, 30, then let's say 15, and so on. This is start. So here, valid position effectively means position can be 1. That will mean at the start. It can be 2. 2 will mean after 10. Similarly, it can be 3 after 15, before 20, after 4, after 5. 1, 2, 3, 4, 5. So a position can be 5 also. That 5 will mean after 30, fifth node will be the new node. Valid position is 6 also. 6 means effectively at the last. This, because valid position. So 6 can be possible. So anything 1 to 6 is valid, and anything other than this are invalid. So for the time being, I assume invalid I am not handling. Then I want to handle this logic. And this needs to be a function. So I will make insert at position some POS. So of course your start will be supplied, your POS will be supplied, and the new value which you want to be inserted, that also will be supplied. What should be the return type? Can be void if the start was not changing. But position 1 will mean start changes. So position 1 will mean start has to be sent back. And if it is to be sent back, in all cases, it needs to be coded for sending back. So node star will be compulsory. Position equal to 1 is a special situation. Even for empty list, that works well. So first, I will always check if position equal to 1. I know what is the code. Either I can write the insert at begin function, or I can write the whole code. But finally, I must write return changed start. And in empty list also, it will work perfectly. So that will be perfectly fine. Else, what to do? So whether you write here the whole code or you write the whole function, and function is called here through one call, is your choice. Else means I have to insert at some other position, which is a valid position, and POS is known to me. So position is always valid. That means I have to insert at some position. Ultimately means I have to bring some my previous pointer to reach to just before that. So how will I start? I will say previous equal to start or head, whatever variable name you have used. So if you have used word start, you will say right start. Otherwise, you can use head, whatever you say. And now, do I need to shift this previous pointer further or not? I will need some while loop to shift further. Ultimately, that will require previous to become previous arrow link. Previous to be shifted to the next node for certain number of times. Once that work is over, now effectively previous points to node after which insertion is to be done. So my previous must point to that place. Then my insert logic, insert after logic can be written without any difficulty. Those 3-4 statements I can write simply. And that will work straight away. But in that case also, don't forget to return the start. Even if it has not changed, but this start return is must because my return type has been specified. So even if it is unchanged, this must be returned because in main, your call is going to come as this call, start equal to insert at some position and whatever being supplied. But it is always being assigned to some variable start. Hence, every call of this function must return even if start has not changed. So this is must. In this case, it changed the start. In this case, unchanged the start, but return must be there. Now, what should be the condition here? So I have to see what should be the condition written. Let's see what I need to do. Think of situation, let's say I'm at node 10. This is my start. So currently my previous is also here. If position was 1, code is separately handled. Let's think if position was 2. Position 2 means after 10 insertion is to be done somewhere here. That will mean my previous pointer is correct. Previous should not be shifted at all. So in this case, previous should not shift will mean that I have no shifting to be done. Otherwise, I need some shifting. How many shifting? For example, position is, let's say, 3. Position 3 means previous should be shifted by 1 level and then the insertion will be done. So loop should work once. So loop has to work once, twice, thrice, or 0 times. So I will take a count variable. That count equal to, let's say, 1 initially. And now I will say count based logic I will write for the condition. While count less than based on some position. If I write count less than position, let's check will it work or not. First time count is 1. Let's say position 2, no shifting was needed. If I write while count less than position, condition is correct, 1 less than 2, it will go inside and previous shifted. I don't want that. So maybe I will say while count less than position minus 1 can be probably correct. Count is 1, position is 2, 2 minus 1, 1. Count less than 1, 1 less than 1, no. We will come out previous points to the node after which insertion to be done. Perfect. If position was, let's say, 4, position 4 meant after 20 insertion to be done. So my previous should go up to 20. That means my previous was initially at 10. I need a 2 shifting. Count is currently 1. 1 less than position minus 1, that is a 3. So 1 less than 3 true. Previous will change once. It will become count should become now increment. So count plus plus. Then count becomes 2 less than 3 true. Count will become 3 less than 3 will become false. 2 shiftings are done. Initially previous was at a 10. After one shifting came at 15. After another shifting reached at a 20. And this is where I wanted to stop. So by writing my condition while count less than POS minus 1 can be okay to do that logic of a previous shifting, previous equal to previous arrow link, and count plus plus. So this can be perfectly fine at this place. And after this, it will work without a difficulty. So this can be the way. So I'm not going to write the full code. Of course, you can understand now you have to practice for this. Similarly, if I say now, just think that for valid situation, it should work. Valid also means if list was empty and insert at position 1 was attempted, it should work. That is also perfect because position equal to 1 has been working without much of a difficulty. So this will work still without a difficulty. Invalid, of course, we are not handling. If you want to handle, you can put additional checks. So invalid additional checks will be needed, maybe in the while loop, else, etc. Additional conditions, additional checks. And you should verify that carefully. So those who want to try, they can do. Otherwise, at least for valid, you should be able to implement. Very similarly, for delete at position P. So delete at position POS will mean if I say POS equal to 1 means starting node to be deleted. Of course, that should work. And otherwise, similarly, the corresponding position. So if my list has, my value list has a 10, 15, 20, 30, 25. If I have this list, then what I'm going to do is, in this case, 1, 2, 3, 4, 5. So my valid position will mean POS can be 1, it can be 2, it can be 3, it can be 4, it can be 5. Any of these can be deleted. So I must write my code for the corresponding cases. Again, function writing, node star will be obvious because in some case position, or in first case position deletion, start changes. So node start will be must, and I must return in every situation. And whatever you want to pass, start, etc., all those will be supplied here. Obviously, I will say if position equal to 1. So the corresponding logic to be written, or delete at beginning or whatever. And finally saying return start. Else I must bring previous pointer to before the or to the node after which it is to be deleted. So bring previous to the node after which node can be deleted, because you need a pointer from there to go to the next. So you have to be on the previous node, only then the link can be updated. So more or less, effectively, it becomes almost the same condition that I can have count equal to 1, previous equal to current or start. If I want to delete the second node, effectively no shifting needed. So that straight away means more or less the same condition, while count less than POS minus 1. Because if POS is 2, 2 minus 1, 1, and no shifting needed, more than that should mean my previous pointer should be shifted. And after shifting, the count should be updated. And that's it. And after that, now delete logic, delete after logic, which we have already done. Those 3, 4 statements, main 3 statements to be implemented here. If the value is also to be displayed or returned, delete value also can be additionally handled. Finally, I must have return start. So that else part will be over and function over. From main, the call will be in the similar manner. It will be always implemented as start equal to delete position at some position and start and whatever POS you sent. And if you want ampersand del val, that also you can do. Start will be always receiving the updated or unchanged start. So start must be returned in every case. For valid positions, perfectly fine. Everything should work. That will mean I must verify that for valid positions, it should work well. I should ensure that. For invalid, if you want to try, you can do your own coding and additional checks will be needed. So now based on that, I will say, let's wind up today's class by giving you the homework for today's class. What is the homework? First thing, I'll say, obviously, the first homework is that I have to implement linked list for insert at position with repeated choices, so that you can try every situation insertion after delete, delete after insertion, insert at certain position, again insert at another position, delete at position 1, again delete at position 1, again delete at position 1, etc., etc. So repeated choices for, let's say, create without create, even I can execute a traverse and then also it should work. Without create, I try insertion at the beginning, that should also work. Or in general, I say insert at position. Delete at position. And this should repeat so that you can test your code for all possible permutations. And some special cases, your code might crash. Like you had 4 nodes, you say delete position 1, delete position 1, 1, 2, 3. Fourth time also position 1 node exists, you should be able to delete. After that, again, if you try delete, it should say deletion not possible. But then if I try insertion, now insertion should work because empty list can have insertion at beginning and all such similar codes. So this is your homework. Practice problem, additional. Those who want to do better programming, those who want to learn more, for them additional practice problem. First, handle invalid situation also for the pose. How to handle? Think of that. Yes, ideally, you should be able to handle invalid through your while loop, etc. itself. Whenever your previous node was being shifted, all those situations you should be able to handle. And remember, position could be given as 0, it could be given as -1, it could be given as more than length, for example, 10, 20, list has, let's say 6 nodes, you gave 10, etc., etc. So you should be able to handle it. With minimum complexity, your coding should remain simplified and readable. So that compromise should not happen. Second, I will say try another. Merge 2 lists of equal length. A simple code I am saying that if my list 1 has, let's say, some nodes x1, x2, x3, I mean, these many number of nodes are there up to xn. List 2 also has some nodes y1, y2, y3, and yn. I have assumed equal length. Then I mean my output should become list 1 should get modified and list 1 now should become alternate connections x1, y1, x2, y2, and so xn, yn. Effectively meaning, let's say if my list 1 is like this, let's say it has 11, it has 21, it has 31, and so and so. So I mean, this is node x1, this is node x2, this is node x3. Then I have list 2. And here I have, let's say 20, let's say 12, 22, 32, and so and so. So this is node y1, y2, y3. Then I want my output to become that list 1 gets correctly now linked in a way that it has 11, followed by 12, followed by 21, followed by 22, and so on. Effectively meaning, earlier you had your linking like this, but now links should be updated, no extra malloc to be done. You have your data in this form earlier available. So what you have to do is, effectively, you should be able to do linking like this. And wherever the list will end. So this will become your list 1, and you should be able to do this. no new malloc to be done. No additional list, current nodes are to be linked again. So this we call as merge at alternate positions or merge alternatively alternate nodes. You should try this. So I will stop here, wishing you a very successful implementation of these homework and additional practice. We are going to strengthen our programming over linked list like this, but basic programming rules are now understood with every one of you. So all programs you can implement knowing these concepts. Let's keep on practicing and learning. Do these carefully. If you have understood these things, remaining 4 or 5 lectures will be very easy to understand and implement, and linked list will become very easy for all of you. So try to do this carefully, and if you have any doubts, next video will show you the solutions also, and you will be able to understand well. Bye-bye. All the best to all of you.